Hi, we should be online now, both on Twitch and on YouTube as far as I'm aware. We will confirm that in a moment. Seems to be, YouTube seems to be online and Twitch is taking its sweet time. But hey, okay. Hi everyone. So, welcome to episode 4 of our string. It seems to be that we've pivoted a little faster than I expected. I was expecting to pivot to another subject next week, but thanks to the time that I found to finish my projects, I was able to, hi Jacek, I was able to move on with my projects faster, and we are able to start the natural language processing / linguistics course this week. So I'm very happy about that and very much excited. Okay, before we go into the subject at hand, again, thank you everybody that supports me and gives me constructive or otherwise any feedback regarding the delivery and the contents that we're covering here. My Patreons that are growing in numbers steadily, that's also very good to see because we're collecting for a camera so you can see me. Without further ado, let's move on to the subject at hand. If you also have any questions, there is Człowiek Wykres, who's our moderator for our channels. So if you have any questions, you can directly ping him and he will pass on the question to me and I'll try and answer to the best of my ability. Alright, so what are we covering today? Today we're covering the introduction to linguistics, so what it is and what you eat it with, as well as some introduction to matrices and introduction to matrices and linear algebraic operations connected with text analysis. Basically, in practice, we'll be looking at how the word-to-vec or GLOV or otherwise word embedding systems are constructed and implemented for us to use. So basically the inner workings of the word embedding systems. We'll look at 2 approaches to it, maybe if we find the time, because we have a lot of things to cover. So we'll see how it goes, but that's the plan more or less. Alrighty, if you have any questions, again, just ask them, and I like the interaction, so you're more than welcome to interact, and that will also show me whether the direction I'm taking is something that is relevant to what you're interested in, and we can tweak it on the fly, because like I said, there are a few things that I want to cover today. Alright, let me make that full screen because we'll be writing linguistics, and my penmanship linguistics, trust me, that says linguistics, okay? So what is it and what do we eat it with and how is it divided? And I'll try to map 3 things. I'll try to map the linguistic domains with the natural language processing domains with the mathematical domains to see how we can go about analyzing and thinking about them in terms of the relationships between them. Okay, so for you that have had any contact with linguistics before, that should be no surprise. Let's divide the science into its domains and we'll try to map it on the fly. Okay, so the first and the most, I'm trying to write my best, the first and the most granular element of the linguistics studies is the phonetics. So phonetics is basically the study of sounds. Now be very careful the way I said it, the study of sounds. So for example, if we have words like teeth, or we have the words like ban and bank. Quick tip, I'll download, I can download, it's actually a pretty neat tool. You will look at the phonetic representations of these words and see what the differences are between, for example, this N and this N in terms of the phonetic That didn't work out quite well. In terms of their phonetic transcriptions, as you'll see later. Okay, so this is the IPA, which is the International Phonetic Alphabet, and these represent different sounds. The N and in the ban and bank are different sounds, and this is what phonetics studies. All right, let me remove that real quick, and we'll move on to the next one. So phonetics is very much interested in how people speak in terms of their individual idiosyncratic expressions of words and pronunciation. So people have different speech impediments, people have different ways of speaking, some people speak faster or slower, and the analysis of this is mapped onto the sound system that we study. Okay, the next domain is phonology. Phonology studies, and this is again very precise, phonology studies the sound system. It's the phonological system that we have in our heads that lets us derive information and understand words, even if they're mispronounced or pronounced incorrectly. We can derive this information by the sound system we have ingrained in our heads in order to understand the speaker, whether they speak clearly or quickly or slowly or slur or do have any other non-standard ways of pronouncing things, let's put it this way. You can see that in a lot of non-native speakers of English or any other language. People tend to say things differently, and we are somehow able to understand them. And that's the study of phonology. So these two map strongly onto forensic studies. When I say forensic studies, it's the speech to text, it's the actual understanding and identifying people by the sound of their voice and the way they pronounce things. So basically how we can identify an individual in order to, in terms of, for example, like criminal activity or something like this. So forensic studies or forensic linguistics, if we eliminate the S, I'm just going to say LGSC, which stands for linguistics, okay? So just use this shortcut. Okay, so this is the study of sounds and sound systems. This is the first group of the linguistic domains. The second group and the third element, for some reason I'm having a lot of delay on this. Okay, it's the morphological studies. Morphology, so this is basically, we can map it onto sounds. This, we map, and we'll need something in between, to words. Yes? So words and the internal constructions of the words. So we're at the level of syllables, we're at the levels of morphemes, so the internal constructions of words in isolation. So we don't combine the words in sentences yet, we don't combine them in meanings, we purely study their internal structure. The way we change, for example, go to going, and the way we change go to goes and go to went, and the fact that the plural of sheep is sheep, not sheeps, and so on and so forth. This is all elements of morphological interest that lies within that domain. We'll get back to what goes in here because that will actually be helpful as we cover other elements. The next level is something that a lot of programmers see whenever they mistype something, is the syntax and grammar. So syntax, again, this will go in here, has to do with sentences. So how do we build sentences in a given language? Is the word order, I'll show you something, important in a given language. So I'll show you an example. If in Polish, Jaś kocha Marysię. Okay? So John loves Mary. There's only 2 ways we can express that in English, but there's at least 6 ways we can express that in Polish, and they all make sense. So, for example, kochajaś Marysię. Again, the same meaning, different word order, same structures, still maps to the same translation. Right? And we can see that we can permute all these words in different orders, and it'll still maintain the meaning because of the flexions, which again are studies that morphology is interested in. Right? Okay. If you have any questions, again, let me know, because this is very much introductory, but very, very important. Okay, the next level, semantics, which is also familiar to programmers in many cases, because even though the program compiles, it sometimes gives the output that we don't wish to for it to give, and this is because of semantic errors or semantic ambiguities. So semantics, basically, is the study of meaning. So what do the words mean? What are the relationships between words? How do we know that this word is related to that one? Is it because of its meaning? Is it because of their relationship? Or is it because of the syntactic, so the sentence structures that we have there? So we'll see how they interact and how these notions and concepts are implemented in the natural language processing practices, so that we can get our beautiful models that give us sentiment analysis and categorize our text and so on and so forth. It's all about the relationships. So in terms of importance for NLP specifically, these two have the greatest impact. So the studies of semantics and study of syntax and grammar bear the most importance here for the NLP. But not only that. Pragmatics, which is another level, is again the study of meaning in context. Yes? So different levels, we speak differently to different people. We speak differently to the elderly, we speak differently to our bosses, we speak differently to our parents and to our brothers and sisters. Hello, Proton. And this is the study of pragmatics. So how do we conduct our day-to-day conversations? How do we speak in an official speech during a presentation? How do we speak to, in different contexts, what kind of elements and what kind of language we use as people to interact and communicate with people? Because this is primarily, but not only, what language is for. Because language primarily and most importantly is to formulate our thinking. There's even psychoanalytical studies that say if you can't verbalize and formulate your thoughts in language, then you're not really thinking. And that's something that is sort of a food for thought, as it were, ironically, because we can't really think without formulating our ideas in a language that we know. Which brings us to another level of the linguistic domain. I'll be sharing this probably, if I can save it somehow, so you can actually see, which is discourse analysis. Imagine the situation where the only way to describe reality around you is the language that you speak. There is no other way to describe reality, and the physical reality and the abstract reality around you, without your language. So that's the only tool you have. For this reason, the reality is determined only by the extent of the productivity of language that you speak. So there are different ways of expressing the same idea and the same reality in different languages. If you think about this, spend about 3 minutes maybe and try to give it into your chat or share it with your chat. How do you say go in Polish? What's the translation of the word go in Polish? What would be the idea behind it? How would you express it in Polish? Okay. On the one hand, while it is real deterministic in its sense that it only allows us to express and describe the reality around us through the language that we speak, there are many languages in the world overall, and therefore the reality, while being deterministic from one point of view, it is actually relative from another, which means depending on which language you speak, that's the tool set that you have, and that's the relativity element that you can express in a particular language. So the way I express and see reality because of the language I speak might be different to another speaker of a different language, which makes it quite interesting from the linguistic perspective on how we study language and how we study relationships with people that speak different languages. So this is actually, we can call it, this is Shapiro-Whorf hypothesis. Don't confuse it with Shapiro-Wilk, which is a normality test for statistical testing, so be very careful here. This is not the same thing. So the idea of determinism, the idea of relativity, is described by this hypothesis. So be very, it's actually a very interesting read when it comes to how you see things. I'll just give you a quick example. I can't really draw a bridge. A very simple thing, that let's call it a road, and there is a dude here, and there is another dude here. This guy's here is different from this guy's here, and it's true for every single person in the world, which means my here will never be the same as anybody else's in the world at any given time and at any given space. So you see how this is relative in terms of the positioning of the physical space and the way language describes it. Okay? So we will now see how these relationships between the time and space and the different words and how they interact with each other come into play to the natural language processing element. Like I said, this is an introductory, not really series, introductory episode to NLP, and we'll be digging quite a few times into this study. But this is very, very important to have in mind as a backdrop to further analysis into the natural language processing elements. Okay. Are there any questions? Obviously, then we can go into neuro, psycho, socio. Yes. Linguistics. So the study of how societies speak, the study of how people think when they speak, what's happening in our brain when we speak, all these different speech, not really impediments, even problems due to brain damage and so on and so forth. All these are studied within the language domain or the linguistics domain. Obviously the study of writing and signs, which has to do with lexicography, graphy, and semiotics. Which is basically the study of sign and the sign meaning, right? So you will talk about what it is in detail as we get to the different meanings of words. But for now, this is, as I said, by means of introduction of how much and how potent the study of language is. I always say that within the studies of signals, the study of language, and the study of vision, we actually are lucky in as much as our domain knowledge is the vision or the language or the signals. So we have very broad implementation capacity when it comes to different projects connected with data science and artificial intelligence in general. Okay, any questions at that stage? Because I want to move on to the mathematics side of things. What will you need in order to pursue the understanding of NLP and how we can go about this? Did anybody come up with the idea how to translate Go into Polish? Nope, nobody has an idea how to say Go. Okay, moving on. It is a tricky question. Let's just put it out there. Okay, so now to the mathematics side. What you will need. Metaphors. Yes, metaphors are the idea under pragmatics. So generally, figures, we call them figures of speech. So metaphors, sarcasm, irony, all these elements that have an underlying tone to the expressions and utterances that people produce are studied within the context of pragmatics. So this is where the meaning in context come into play, right? So for example, if I say this food was really delicious and I pull a face, then we know that what's happening. We know that we don't really mean it. We don't actually mean it sincerely, at least. Okay, today we're going to cover only one tiny bit of mathematics that will help us build the word embedding systems, which is linear algebra. See, each. Okay. Right. Linear algebra today, but we also need probability, a tiny bit of statistics, and for now, for the purposes of this series, no problem, Mateusz. For the purposes of this series, this should suffice for now. But as we move on, we'll add more and more elements to it. So if you don't know what to do at your weekends or during your weekends, study those three things because we'll need them to build our models to begin with. Okay. So this is by means of introduction when it comes to linguistics. And I don't think there is much more to add at this stage. Okay. So today we're going to, I'll share this board as well. Today we're going to look at two texts really. We're going to be looking at, let me just import NumPy because NumPy will be our linear algebra element. As NP will import, what's this? Overwrite, yes, overwrite please. I don't know what's happening, okay. We're going to need a counter to basically help us count the number of words in different texts. This is a simplistic solution. This is nothing. We're not losing any knowledge because we're using this. We could implement it otherwise or more granularly, but there is no point. And I'm gonna also import warnings because I don't want you to see the screens. Build warnings. Yes, I can zoom in a moment. Yes. Ignore. Okay. That should be all right. Is that good enough? Or should I make it even? Is that good? Okay, I'm going to assume it's good, and if not, just let me know. Okay, so we're going to be looking at one text that is from an economic field and one text that is from machine learning field. And we're going to be looking at how contextual relationships between words create the word embeddings that we know. Perfect, thank you. Anything to make your life easier. Okay, so we're going to open the first text and we're going to call it econ simply because it's okay. All right, it's okay. I'm going to say it's okay. So let's open, I think, NLP, week 3, I think it was. Yes. So I actually have economy, machine learning, and then TikTok, but we're not going to use the TikTok today. We're going to save it for next time because we might run out of time. Okay, so we're going to econ.txt and we're going to read it in and then count the words. Word count from economy, counter, just really quickly, econ read. This is just preparation, I'm not explaining much because I'm not doing anything magical here. Count, of course not. Yes, and we're going to do the same with the second text, and we're going to try and compare them and talk about linear algebra a little bit more. Okay, so we're going to call it ML for machine learning, and we're going to do the same thing, and it was ml.txt. Okay, just read it in, and then do machine learning, the word count for machine learning, which is counter ml.read. We're doing exactly the same thing, splitting the words and then reading them in ML. Okay, so now what we've created, we've literally created a word count. If I just show you, we've created a word count for each of the words that are happening. We're not talking about how to clean this text today yet. We're going to be studying that in depth as we talk about morphological studies and what we can get rid of and what we can't and why in terms of the meaning and sense of meaning for different contexts. But today we're not dealing with that. This is just an example of how we can simply create a word embedding based on basic linear algebra. Okay? So let me clear the output. I'm going to create a, let's see how many words maybe. Okay, quickly. Len of, we have 743 words in the first corpus, and I should explain corpus. Whenever I say corpus, that means text or document. And you'll hear me say two things in terms of plural. You'll hear me either corpora or corpuses. If you read any text about NLP, you'll probably see corpora more than you'll see corpuses, but both are used interchangeably and equally as fine. Okay, ish. Okay, I see this. Okay, keep it coming. Let's see who else can come up with a good translation of the word go into Polish. All right, and we're going to do, and we have 1206 words in the machine learning text. I'll share the text with you as well to see how it goes. And we're going to be looking at a relationship between two words. We're going to be looking at the relationship between the word data and analysis. Okay, so what is the relationship between those two words and how we can measure the relationship mathematically? Okay, so if we look at the key data, We have 36 times that it's happened, that it occurred in this text about economy. And similarly, 23 times it happened in the machine learning text. I've chosen them specifically, I counted that before, simply because I needed to have a good representation, so I needed to scroll through some text to get it right. And by the same token, we're going to look at data from, analysis viewers. Analysis 2 times only in the text about economy, and 11 times in the text about machine learning. Okay? So now, how does it work? Let's create a vector, and we'll talk about vectors extensively. This is again more of a demo than it is anything else. So a vector from economy, from the 2 words that we're analyzing. So we're talking about data. So let's borrow this here. And let's just type it out, it's quicker, analysis. Okay, close this. I don't really, yeah, I do. Okay, so econ of vec looks like this. It's now a tuple of the size 36 by 2. Okay, so let's convert it to a NumPy array because we want to do linear algebraic expressions about them or analysis on them. Okay, and now it's an array, which is what we want. We're going to have to do the same thing here, and we're going to replace, simply just replace econ vec with ml vec with any luck, and we'll take ml. I should have switched that as earlier. And we have our array of 23 by 11 when it comes to the representation of the vectors. These are by definition column vectors, so if you were to represent them mathematically, they would look like this, and 23 by 11. Okay, these are column vectors, not row vectors, even though they look slightly differently. Okay, so beware of that. This will come as an importance later. And let's concatenate them together. I've prepared some, let's say, utility functions to speed up the process, because I don't want you to see me code all the graphical representations of it, and I have a utility file that I use in all my projects when it comes to vector visualizations. So if you don't mind, I'll help myself to those. So all the vectors, let's just combine them, okay? So we're gonna use and it's gonna be econ vector and an ML vector, okay? All right, looks good. So we're getting there. And I'm gonna now borrow this piece of code to speed things up. PLT, yes, of course. Okay. And these 2 vectors look like this. Wleść, obchodzić się, zmieścić, okrążać, prowadzić, dokądś, zabierać. You see, and let's summarize this poll a little bit here. Iść, pójść, pojechać. You see what I mean? every single word in Polish implies some kind of manner of movement. Because iść means to walk, pójść means to walk, pojechać means to drive, chodzić means to walk, jeździć, and so on and so forth. There is no one generic translation in the Polish language of the word go. All these words mean the word go if you put them in the right context in English, but there is no direct translation between them. This is exactly what I mean by relativity. And there is also phraseological expressions that combine with the word go that we would never even think of in Polish. So very good, thank you Mateusz for checking this, and this is exactly my point. We don't have one word for the word go, even though we have all these expressions to describe it in many different ways and manners. Alright, but getting back to the subject at hand here, when it comes to the similarity and the relationship between them, we will look at two things. We will look at the angle between them and what the angle is and how close they are to each other, and we'll be discussing linear algebra in very much detail because it's really, really crucial here. And we'll be also looking at the distances between them. And these two metrics tell you how close or far away two different word vectors are in a different context, and whether there is a relationship between them. Okay? So this is what we'll do. Again, by means of a demo today, and we'll dig deeper into the studies as we go along. All right, so the first thing that we'll look into is what we call dot product. The idea behind the dot product, we had 36 and 2, and we put a little circle here to manage this, and I think it was 23 and 11. Basically, we take these two elements, multiply, and add these two bottom elements here, row by row, column by column, 2 times 11, and we sum them up, and we get a number that is in our R. And what does this number mean? This number is exactly telling us, if we scroll back a little up, can we? Yes. If we scroll back a little, tells us if it's positive, it will lie, if we just add an arrow here, sorry, a Y, and this is, let's say, X, tells us where it lies on our coordinate system. If it was negative, it'd be somewhere here. But we never have a negative here because we don't have negative number of words here. So it'll always be in this realm here. So in our case, it'll always be positive. Why do we need this? And how do we do this in NumPy dot product? And this is where matrices come into play, and matrices being very important. I'll show you 4 different ways on how to do it, and we're going to call them different ways. Let's just create 2 random array, and let's call them 0, 1, 2, 3, and then 2, and then 4, 5, 6, and 7. So I'll show you how to do the dot product real quick. Yes, good job, Mateusz. Yes, very much so. So they come in 4 different flavors, and I'll show you. The first one will be the noob way. Don't do it. Okay? For A and B, and we do NPRA1, NPRA2. What we could do is, I'm going to call it flavor 1. Flavor 1, so one way of doing it. And let's just do A times B. Avoid this like the plague. If you can, stay away from for loops in data science. They're slow. Don't do it this way. Okay? Flavor 2. Recommended. And we'll discuss this in detail. And flavor 2. 2 np dot, and we're doing np array 1, np array 2. Okay? Flavor 1 is not defined. Oh yes, because we also need flavor 1 is equal to 0. Okay, so we get our, we get our dot product from these two vectors. Okay, flavor 3, also very important. The equal, let's call it, because you don't see it very much, and you should. Flavor 3 is np array 1, and we put an @ sign there, and we get 38 as well. So an @ sign also gives us the dot product of the two vectors. And the okay way, but meh, let's call it this way. So you could do it this way, but why would you? Which is flavor 4. And this would be, we sum the multiplication of the two products. Flavor 4. Okay, we also get the same thing. So again, this will be shared on our GitLab, so you'll have access to it, how to do the dot products. Why do we need it? Because we'll be calculating, as I said, the angle here and the distance here between those two. Sorry, my drawings, I'm not Rembrandt. And this would be our cosine similarity. So how big is the angle between these two vectors, or how big is the cosine between them, and what would be the distance? And that's how you determine the relationship between words given a particular context of documents or other words that are around it. It's the same technique, same idea. Just you give it different data. And how do you do this? We basically take the dot product. So basically, our two vectors that we've created earlier, and we take their norm. And again, all this will be explained in the future, but norm is basically the length of those two vectors. Norm is usually called, it's usually called because it's part of the NumPy, and it's usually what's used in literature. Okay, so how do we do this? Cosine similarity of vectors A and vectors B, vector B. Okay, so first, like I said, let's just maybe keep it for our reference. A times B, vector, over the A and the norm B. Okay, for our reference, we're literally translating this formula into code. So the dot product, as you saw, A and B, the norm of A, and then we have norm of B. So the norm of A, we take A, linear algebra norm, B, and we literally compute the cosine. Norm A times norm B. I'll show you, maybe I'll show you, maybe I won't, I will see. And then we just return the cosine. And we would need some kind of documentation here, and I'll add it later. Dot, yeah, I need an equal sign here. Okay? So with that in mind, we have created our vectors. Cosine, similarity, and we had our vectors here, the ones that we've created. So one of them is econ vector, economy, and the other one is machine learning, and we're literally trying to compute these two vectors. These are the representations of the two vectors. So basically we're taking the econ vector and the ML vector. Okay, and we get this number. Maybe we can just ground it, just to 2. Yeah. Okay, and we get our value 0.2. So this is the cosine of our angle alpha, 0.2. This is not the angle itself, this is not close to 1, but if you think about this, as it progresses, the closer to 1 it is, sorry, I just drew a different function. The closer basically you are to 0, right? The more likely it is that we don't explain things very much, and the more distant they are. And we'll talk about this more and more in the episodes to come. Okay? So we now know that there is some kind of a relationship between them, but we could definitely bring this one closer. And we'll have probably other words that will be lying on the line more and more. The closer they are together, the more relationship is between them. Okay? Okay, the second one is the distance, Euclidean distance, right? So what's the difference between them, between those two coordinates? Okay, so we'll do the same thing. We'll just define an Euclidean, maybe just simply. And again, two vectors, and we return a d, which basically is our measure, or any distance, right? And again, linear algebra, we take the norm. I haven't explained it, I'll explain it in a moment, and we take the difference. Okay, distance. So what happened here? The length of our vectors, it was 36 and 2, is basically come on, you can write 2. All right, this is how you calculate it. That's the norm. Okay, I don't know what 36 squared is in my head, but this is how you do this. And we literally calculate the norm of the difference between the two vectors. So if you come back with me to the drawing, to the visualization, we take the difference, so we literally subtract one from the other and do exactly that. Okay? And again, this will be explained and fleshed out in detail in the course, in the episodes to come. But right now it's just a demonstration how easy things are when it comes to implementing word embeddings, and how easy it is for us to manipulate this, provided we have some background knowledge about linguistics and the mathematical implementation. So we have the Euclidean of, again, econ vector and ML vector. And we get our value. Okay, as we have more vectors, this was just 2 words that we just gave an example of. We can have 1,500 different words and create relationships between them. You can have multiple dimensions, and they all basic mathematics that I just showed here applies just the same. The studies that we've shown and the domains of linguistics that we've shown allow us to do these mathematical operations to a certain extent, by which I mean there are certain elements that we cannot compute mathematically simply because language does not work in such a rigorous way as mathematics does. So certain elements cannot be expressed in this way, and that's where you see NLP failing in many contexts, not being able to properly translate things the way a human would, and so on and so forth. But to the extent that we can manipulate and codify language and translate it into the language of mathematics, that's how far we were able to take it so far in the realm of NLP and linguistics. Okay. Excuse me. Are there any questions about this? I know there is a lot of a few things that have shown up here that may not be particularly clear from the mathematical standpoint or the linguistic standpoint. It is my goal to further delve into the linguistic element and the mathematical element to see how they relate to each other and how they intertwine and interact with each other. For now, today, this was a short presentation on how you can see these words relationships and these word embeddings and word relationships, and what? And are there any questions about what just happened? Do you know what word embeddings are? What we've created just now is basically we've created a mathematical relationship this is not a mathematical symbol here, I'm just showing the relationship. And we know that the cosine similarity is 0.92 and the Euclidean distance is 15.81. If you are ever looking into the GloVe or Word2Vec implementations or word embeddings in general, you'll see exactly those numbers. These are the numeric representations of the numbers that are encoded in the word embeddings and pre-trained for us to be used in other contexts, so we don't have to waste time to train the neural networks or other models on languages because we don't want to waste that time. There are other people that have done it for us and have done a massively extensive work on codifying these relationships and creating them exactly in this way. So basically what they've done is computing the cosine similarities and the Euclidean distances on God knows how many words and God knows how many relationships that they tried to come up with. The top that we have so far is the relationships work on any space, in any vector space. Like I said, the top we have here now is GPT-3, and these have, I think, these relationships are, 175 billion weights. So these work on in all dimensions. It's very hard to visualize this in more than 3 dimensions because we don't have that capacity as much as we'd like to. But numerically and mathematically, we can operate in 5,000 dimensions or 100,000 dimensions or 600 million dimensions if we would want to. Mathematically, we are able to do that, but not necessarily visually. So these relationships apply to all the relationships that you can create. The relationship studies I'll show you next time, but just to give you a little teaser. I go home. Okay? We can go this way, or we can go this way. The idea is, what can we put instead of I? What kind of words? It's hard to imagine. It's impossible for us to imagine anything. We could potentially imagine a 5D manifold or something, but it's very hard to see them. But yes, mathematically and intuitively, we are able to translate 2D or 3D onto 100D or 200D. This is the tools of linear algebra that allow us to do that. So mathematically we're able to, but visually not really. What can we replace? So coming back to this, what can we replace with the word I to make for the sentence to be still grammatical? What can we replace with go for the sentence to be still grammatical, and so on and so forth? What can we put after go for the sentence to make sense? Or what can we put before go for the sentence to make sense? This is how it's built. And this is actually an idea from 1930s, right? It's the syntagmatic and paradigmatic relationships that have been created by a guy, Ferdinand de Saussure, a Swiss guy as far as I remember, but I might be wrong, on how these relationships work. And we now use this idea from 1930s to implement our word embeddings and create our relationships, both from this the syntactics of the sentence construction elements and the semantics, so the meaning of words and the relationships between them. And we can do that mathematically. So an idea that came up soon to be 100 years ago now finds its applications in natural language processing. Okay, so this is by means of introduction. What we'll cover still is we'll cover the more linear algebra. We'll cover the text, so this will be used for word sequencing. We'll cover more probability. This will be for our text classification. And we'll be doing all this. We'll cover most of the ideas that are hidden behind NLP, so machine translation, text classification, sentiment analysis, text summarization, search engines, all that stuff we'll cover from the perspective of language and from the perspective of analysis. So this should hopefully give you an idea of what's about to happen. Are there any questions at this stage? Because we've exhausted our hour, and I want to stick to the hour in terms of the length of the stream. So are there any questions? Is there anything else that I can explain or expand on that you would like to know more about before we delve into the elements, or before we break the NLP down into pieces and see what's inside? I'm going to take a sip of tea because no more questions. All right. In that case, thank you very much, and I shall see you next Thursday for the English stream in terms of coverage of the natural language processing. I think what we'll start with is the text classifications elements. We'll talk about probability, and we'll talk about the modeling on how we can actually implement the machine learning models, not necessarily the deep learning models yet. We'll look basically on how to implement things like logistic regression and naive Bayes classifications for the texts, and then take it from there. All right, thank you everyone. If you have any questions, we actually have a Discord channel that is added to the link in the description of the video. I'll share the notebook with you, and this book, that if I manage to download it, I'll share it with you. And also on Monday at 6 p.m. CEST, we'll have our Polish stream where we'll continue our fights with pandas. Okie doke. So thank you very much,